So, welcome everybody. It is my pleasure to introduce Shea Garrison-Kimmel. Shea did his undergraduate studies at Haverford and then went on from there to do his PhD at UC Irvine with James Bullock. And from there he went to be an Einstein Fellow at Caltech and is currently there, still as a postdoc. And Shea's been doing really phenomenal work on the local group, and he's going to show us really awesome movies about all the things going on in our local group. And specifically, he's really been tackling some of the most challenging questions we have right now in cosmology that you can answer with low-mass galaxies. So, take it away.
Thank you, Bettina. All right. So thank you guys all for coming out. I appreciate you having me here. It's been a great visit so far. Before I get started, I of course want to thank all my collaborators. I should probably mention, in this movie that you guys have all been watching, on the left here you're seeing gas, with green being roughly warm gas, purple cold gas, and red hot gas. While on the left you see false color images of the stars. Doesn't really look like false color down here just because it's so zoomed out. Okay, so before I really dive into my talk, I of course want to thank all my collaborators. Oh, color's a little weird on this, that's okay. So of course this includes all the wonderful people on this slide, but I also want to give a shout out to the entirety of the FIRE collaboration. This is just chock full of about 75 people at this point total, just combining their resources, be it computational, person, whatever, and coming up with really awesome, fantastic results in terms of galaxy formation. So because I'm going to kind of cover a lot in this talk, I want to give you an idea of the narrative structure. I'm going to start just by giving an overview of the standard cosmological paradigm and some of the small-scale problems within that, which will lead into the questions that motivate my research. Then I'll move into some insights that we've gleaned from the simulations I've run of the galactic neighborhood, of our galactic neighborhood, which will introduce next-generation simulations of the local group, which is the main thing I want to talk to you about today. And then finally, I'll close with a brief discussion of where I see roughly the next 10 years of near-field cosmology going. So, for the standard cosmological paradigm, I find this pie chart to be the most important piece of that, at least. So this is giving you, of course, the composition of the universe today as we measure it on very, very large scales. However, what I want to focus on are the green and orange parts of this pie chart, the dark matter and the baryons, which are basically to say the gravitating mass. And what I want to focus your attention to is, of course, the dark matter is 87% of the gravitating mass in the universe. Baryons are a small perturbation on top of the dark matter when it comes to gravity. Right? So it's entirely reasonable to ask, what does the dark matter alone give us? And part of the reason that we want to do that is because baryons are really complicated. Right? So all these images that I have up here, these are examples of baryonic physics. So by baryons, I mean standard model particles, basically. So you have clusters of galaxies, you have star-planet configurations, you have mountains, plant cells, single hydrogen atoms. But the physics that govern all of these things are incredibly varied and incredibly difficult to do on a computer, especially if you wanted to do them all together. On the other hand, gravity is extremely simple, right? To solve gravity on a computer, all we have to do is a multipole expansion and let time run forward, basically. Of course, if we want to allow time to run forward, we better start with some initial conditions. So this is what we think the initial conditions of the universe looked like about 200 million years after the Big Bang. Here, light regions are basically higher density, so more mass. And then, because baryons are a minuscule perturbation on top of the dark matter, we're going to do a gravity-only simulation here. So if we start running the clock forward here, then what you'll see is what we call hierarchical structure formation, right? So small objects collapse first, small clumps of dark matter that we call halos collapse, and then they merge together, for example, in this big region here. So large overdensities become more overdense, while large underdensities, these orangish regions, become more underdense. And if you run this all the way to the present day, then what you find is a picture that looks something like this on very large scales. Right? And again, this is gravity only. We're ignoring all the other physics that go into baryons. But nonetheless, let's ask, how does this picture work? If we take these clumps of dark matter and we just paste galaxies on top of them, do we do a reasonable job of recovering the model? Now, of recovering the observations with this model? Now, this is a huge chunk of the universe. This picture is about 800 million light years across. Okay? So let's compare to a huge distribution of galaxies. That gives you this famous plot that I'm guessing a lot of you guys have seen before. So in yellow here are the observations, And in blue are what you get when you paste the galaxies on top of this gravity-only simulation. And if I hadn't told you which was which, you probably wouldn't be able to tell. And if you apply statistical analyses to these two distributions of galaxies, so each dot here is a single galaxy, then you find basically the exact same answer. So in other words, this model is remarkably successful on larger scales. It does an incredible job at reproducing the observations. But this is a huge chunk of the universe, 800 million light years across. Our galaxy, the Milky Way galaxy, would be smaller than a pixel on this image. Right? So let's zoom in on a chunk of the universe that we think hosts our galaxy, the Milky Way. So this image is showing you what the model predicts for a much smaller scale galaxy. So here again, this is a gravity-only simulation. So again, I have to paste the Milky Way in here. So if I do that, then the Milky Way lives in about this little tiny box here. So again, we're still looking at pretty big scales. This is, cosmologically speaking, relatively small, but galactically speaking, this is still quite large. So the sun would just be a tiny bit offset from the center here. Okay, so I want to now quickly take a quick deviation. I had to paste this galaxy on top of there, so let's talk a little bit about the physics that have to actually go into creating that galaxy if we wanted to do it self-consistently. Well, a galaxy is a factory that turns gas into stars. That's all it does. So we better start with some gas somewhere. So in this picture, the halo has mostly already formed. The gas is sort of hanging around the outskirts, and then gravity makes the gas fall into the center of the halo. But after that, other physics takes over, and we have to start accounting for that other physics. So first, the gas we think is going to shock heat. That makes it expand to roughly fill the halo. But then, it's able to start cooling. It can emit radiation, so it can cool down, so it can lose some pressure support. But it also has angular momentum, so when it cools down into this disk. And of course, this is not to scale. Then that disk of gas can start forming stars, and voila, we have a galaxy. Of course, it's a bit more complicated than that because these stars then do things. So some of those stars are going to, for example, blow up in supernovae that affect the environments around them. All of them are going to be pumping out radiation. And all of this feedback together can do crazy things like drive outflows and regulate your star formation rate. So to give an example of just how crazy galaxies are, I like to show this giant swath of things varying from these mergers here to flocculent disks to these big outflows that you see around some certain galaxies. But all of these are the same class of object. These are all galaxies, by which I mean that they're all stars and sometimes gas that are gravitationally bound together by an underlying clump of dark matter. So that's the definition of galaxy I'm going to use for the rest of this talk. Now, if we return to this picture, we put our Milky Way at the center of our dark matter halo, then you might say, okay, this clump here hosts the Milky Way, but what about all of these little clumps out here? Well, in the standard paradigm, we think that those host dwarf galaxies, which are, again, galaxies in every sense of the word. They're clumps of stars and sometimes gas hosted by a dark matter halo. But as you can see from these pictures, they look nothing like the galaxies I showed you on the previous slide, right? So something like the Large Magellanic Cloud, this is sort of the biggest dwarf galaxy that we consider. This has about 1% the mass, 10% of the stellar mass of the Milky Way. Then you walk down to things like Sculptor, that are about 1 million stars, Carina, that's closer to 100,000, all the way down to things like Woman 1. I can't see a galaxy here, but there is a galaxy in this image, I promise you. Just to really drive that home, here are all of our normal galaxies, right? Things that you have a picture in your mind of what a galaxy is. Here are the things I'm going to be talking about for the rest of this talk. Okay, now why talk about dwarf galaxies? Why are they interesting? Well, they're very low surface brightness, right? So they're really hard to study. But as a counterpoint, they come with resolved stellar observations. So we can see individual stars, and we can ask what those individual stars are doing. Glad a couple people are laughing. Now, of course, the downside, again, is that we can only really do this in the nearby universe, out to about a megaparsec or so. And if that were all it is, we'd say, okay, well, these are interesting objects. They're galaxies, and we want to study galaxies, so we should study these. But there's more to it than that, actually. So number one, these systems are the most dark matter-dominated objects in the universe, and therefore they're the most sensitive to dark matter physics. Right? So when we change the physics of dark matter, we expect it to show up strongly in dwarf galaxies. And number two, By definition, dwarf galaxies are the smallest bright objects that probe with dark matter. Therefore, they're the smallest objects that probe the standard cosmological paradigm, and therefore they probe the scales where the model is the least constrained. Because remember that pie chart I showed you at the beginning, that's coming from very large scale observations. In fact, we were talking just a few minutes ago, we think that goes down to about cluster scale. Okay, so what are some examples of what we've learned from dwarf galaxies? I'm going to start with a problem that many of you have probably seen before, the missing satellites problem. That basically says that if we look at this picture of our Milky Way halo again, then the theory tells us that there are thousands of subhalos. And it's kind of hard to see on this, but as you go down to fainter and fainter on this image, you just see more and more little spots of light, self-bound clumps of dark matter pop out. Then you go and you look at the observations, and you find of order 10 to 30 dwarf galaxies around the Milky Way. Right? So this problem, the missing satellites problem, can be summarized by saying the simulations predict too many clumps. Right? Now there are a lot of ways to get around this. People recognized pretty quickly that you can invoke physics that explain this rather naturally. I don't want to get into what that physics is, but I'm happy to talk about it later. But the basic summary of that is that maybe a bunch of these clumps are too small to form stars, or at least too faint for us to have found. Right? So the missing satellites are there, we just haven't found them yet, or they're dark clumps without stars in them. Now, this is well motivated from higher masses. So this is an example from Peter Baruzzi's 2013 paper. This is plotting the stellar mass of a galaxy on the y-axis against the total halo mass, which again is going to be mostly dark matter, because dark matter dominates the gravity. And you can see that there's a pretty tight, with relatively minimal scatter, relationship between these two. But again, to give you a sense of scale, up here we're looking at galaxy clusters. Here we're looking at about the Milky Way, where this turns over. The LMC, the Large Magellanic Cloud, would be about here. And the systems that I care about, dwarf galaxies, these tend to lie basically off the plot here. Right? So while there's a lot of motivation from higher masses, that stellar mass and halo mass are closely related, we don't necessarily have clear proof of that at lower masses. Nonetheless, let's go ahead and extrapolate this relationship. Any reasonable extrapolation is going to say that the biggest dark matter clumps, the biggest subhalos, should be hosting the brightest satellites, right? That's what you get if you just naively extrapolate a relationship between stellar mass and halo mass. So, let's ask the question, can they? Are they hosting the biggest clumps? Are they hosting the brightest satellites? So in order to do this, we're going to look in terms of structure of these systems. In particular, we're going to look at the rotation velocity radius plane. So this is basically enclosed mass on the y-axis. Here we go, enclosed mass on the y-axis, and just radius on the x-axis. And now for these galaxies, these are dispersion-supported galaxies. So an observer can go out, they can get line-of-sight velocities for a bunch of stars, do a bunch of really hard work to reduce the data, and then they get to put a single point on here for a single galaxy. Okay, then you go out and you do that again, you do a whole bunch more work, and you do that 9 to 10 more times, and you get to fill roughly this space of the plot with the observations. Now in the simulations we know everything, right? We know the entire mass profile from basically our resolution limit out to infinity. So instead of plotting a single point, we can plot lines. And when we plot the circular velocity profiles of the biggest subhalos in these simulations, what you see is that they have too much central mass compared to the satellites that we expect them to host. Okay, so this has also been called the too big to fail problem. I'm going to try to refer to it as a central mass problem because I think that's a bit more intuitive. But the reason we call this too big to fail is because we say that these massive subhalos are too big to fail to form stars, yet they have no clear observational analogues. So what do we match these things with? This also is related, for those of you that are familiar with it, this is related to the cusp core problem, but at sort of different mass scales. The basic gist is that in a lot of galaxies, the standard cosmological paradigm predicts too much mass at the center relative to observations. Now there's an enormous caveat to this, right, that I haven't really been emphasizing, and that's that these simulations are gravity only, right? And I told you earlier that we need additional physics to form a galaxy. Now, the standard assumption was that these galaxies are small enough and dark matter dominated enough that the baryons probably wouldn't matter, but maybe they do, right? Maybe they do. So the question that implies is which non-gravitational physics are important? Is it baryons or is it new dark sector physics? In particular, this sets up my burning questions of what physics are required / allowed by the dwarf galaxies of the local group, what crazy dark matter models help us to match the observations, what crazy dark matter models are completely excluded, what reasonable dark matter models are excluded. Is stellar feedback important with only 1 million stars? These are very small, very dark matter dominated galaxies, so do we need to worry about the baryons? And number 2, how do galaxies, particularly dwarf galaxies, form and evolve? How important is their environment and what does their environment do? And can we predict their evolution from their initial conditions? Now, before I really dig into that, I need to show you one more piece of background that I've been kind of hiding from you. So I told you earlier that we can well study dwarfs out to about 1 megaparsec. But this picture here is about 300 kiloparsecs in radius, right? So if we zoom out from this picture, then we find that the Milky Way is not really living alone in intergalactic space. Instead, it's in this region of the universe that we call the local group. And that's important because the local group contains the Milky Way and all of its satellites, as well as Andromeda, a relatively massive galaxy, actually slightly more massive than the Milky Way itself, that's pretty close to the Milky Way. So I've drawn these circles such that they're not quite overlapping. We think that's about the state of the field today. And so Andromeda, as a massive galaxy, as an L-star galaxy, has a lot of its own satellites, actually even more than the Milky Way. But then in addition to the satellites of the local group in M31, we also have all of these non-satellite galaxies down here and up here. So these are dwarf galaxies that are not satellites of the Milky Way or M31. At least not yet, or not today, I should say. So if we want to study the local group as a whole, we should probably simulate the local group as a whole. So as a graduate student, I led the Elvis project, which stood for Exploring the Local Volume in Simulations. So we simulated 12 pairs of Milky Way and Andromeda-like systems. And then to go along with that, we came up with a set of mass-matched isolated halos, non-paired halos of identical mass. Excuse me. Now just to give you a sense, this is what the full sample kind of looks like at redshift 0. So this is a dark matter structure predicted by the standard paradigm around the local group. So in each of these, of course, we have a Milky Way and M31, but in some cases we have, for example, an LMC. In all of them, you can see there's a lot of structure just completely filling the volume. So now that we have the statistical suite of simulations, we can start to ask questions. For example, what does this relationship look like at lower masses, right? I argue that this works great everywhere that we basically plotted here, but we don't know how to extrapolate it. Now what we showed is that if you make just slight tweaks to the inputs to that model, then you get this relationship here that does a really good job of reproducing the observations. So on the left side here, I'm plotting a stellar mass function. So the y-axis is the number of galaxies larger than a given mass, while the x-axis is the stellar mass of a given galaxy. The blue line here is the observations in the entire local group. The white and green lines are the predictions from the simulations. Once we apply this model to those simulations. Remember, these are gravity-only simulations, so we have to paste galaxies on top. And I would argue that this does a really good job of matching the observations. Now, that said, I've intentionally left this half of the plot blank, right? And the reason is because if I go to fainter galaxies, lower stellar masses, then of course the observations tail off. Now we think this is probably just observational incompleteness, right? These galaxies are very hard to find. Fortunately, LSST, which I'll talk a little bit more about later, is coming online soonish. We think that this will start to bring this line back up into agreement with the predictions, but if it doesn't, then we're going to have to invoke some new physics, something that changes the behavior of this line on the left at lower masses. Okay, so great, we match the observations in terms of galaxy counts, right? But I spent half of my introduction telling you about how even if we assume, or even if we're able to match galaxy counts, we do so by not matching galaxy structure, right? If you remember the central mass problem, this plot here, then this doesn't work, right? So does this work? Well, the answer is no, of course. we found that the central mass problem is ubiquitous throughout the local group. So this is showing the dots here are local group galaxies again. This is now a different sample. I'm looking specifically at non-satellites here. And you can see that, again, they're just a plethora of relatively high mass dwarf halos that have way too much mass at their centers to host the vast majority of the local field, in this case, dwarf galaxies. So this tells us that one-to-one matching doesn't work, and it also tells us, or that some sort of non-gravitational physics is important, right? So let's start with that first assumption. Let's break that assumption of one-to-one matching. So, to do that, I want to show you this plot. This is two different ways of assigning stellar mass to a dark matter halo. The cyan line has exactly 0 scatters, perfectly one-to-one. The magenta line has 2 decades of log normal scatters. So this is an enormous amount of scatter, 10 times what's reported at higher masses, basically. And somewhat surprisingly, if we applied both of these relationships to the Elvis suite, we're able to recover within roughly Poissonian error the local group stellar mass function with both of these relationships, right? So you might be asking, well, wait, how does that work? How can both of these give you the same stellar mass function if they behave so differently in terms of stellar mass, halo mass? Well, to give you an idea of what's happening, let me show you what happens, what you get if you don't include the scatter from this magenta relationship. Right? So here you predict about 1/3 as many galaxies as its mass. And the reason is because there are a lot more galaxies down, a lot more halos down here that have the possibility to scatter up in stellar mass than there are halos up here that have the possibility to scatter down. So if we make the scatter bigger, then we have to make the slope steeper, right, in order to still reproduce galaxy counts. Now, what does this mean in terms of the central mass problem? Well, this enables us to put some of the observed local group satellites in relatively low mass dark matter halos. Low mass dark matter halos have less central mass too, so this helps with the central mass problem. But that said, even this model with 10 times as much scatter as what you see at higher masses is not enough. You still, on average, find a central mass problem.
So just to be clear, you're not saying that you're applying a different weighting above and below your magenta line. You're just saying the absence of anything at the top end means that you're going to have more room to see. I guess I'm a little bit confused by you saying more things scatter up than down.
Yeah, so your halo mass function, as you go down in halo mass, rises steeply at about dm by dm.
So your counts are just much higher at the bottom end.
That's right. Yeah,
but
so
those could still scatter in either direction.
That's right. So there are plenty of low mass halos that are hosting galaxies down here, and that's fine. They just don't show up. Nice. Right? They haven't been found yet, basically. And similarly, some of these high mass halos would also be living down here, and so we would say that we haven't found those either. It would probably help if I put a horizontal line at about 10 to the 5 here. Yeah. So this is sort of smashing together the halo mass function and the stellar mass halo mass relationship. So if what we're seeing isn't due to just halo to halo variance, or at least not entirely due to halo variance, maybe this is telling us something about baryonic physics, right? To give you an idea of what I mean by that, first example at least, I want to show you this movie. We were promised movies, so I'll show you movies. I want to show you this movie from the fire simulation. So this is a simulation of an isolated dwarf galaxy. Has gravity, of course, but here we've also turned on hydrodynamics, we've turned on star formation, and we've turned on stellar feedback, in particular supernovae. And what you can see is every so often there's going to be a wave, effectively, that comes out of that central galaxy of hot gas, right? There was one right there, there's another right there. And what's happening here is basically, so the gas falls into the center of the galaxy, cools down, fragments, forms stars. Those stars live for 20 to 100 megayears, and then they blow up in supernovae. And because it formed a bunch of stars at once, a bunch of supernovae blow up at once, right? Which means that you have a lot of energy coming out all at the same time. So that energy is able to couple to the gas and drive the gas out of the halo, because these halos are so low mass, they have a relatively shallow potential well. And when that gas flies out of the halo, it's able to carry some dark matter with it. Now, I think there's increasing agreement among simulators that this does happen, and that this does modify your dark matter halo. So on the x-axis here, I have the stellar mass basically increasing to the right. And on the y-axis, basically read this as less dense up here and more dense down here. And what you can see is as you go, there's basically a peak here where you have enough stellar mass that you're able to effectively lower your central mass. Whereas down here, you don't have enough stars to do anything to your dark matter. And up here, you have too many baryons, so you make your potential well even deeper, right? But there's a sweet spot where you can form what we call dark matter cores, so you can lower your central mass of your halo. That said, in terms of the central mass problem, those galaxies kind of live right around here, where some of them have lower densities, some of them have what's predicted by the standard paradigm, so it's really not clear. We need to run basically a much larger simulation that includes all of these in one run rather than disparate simulations. So again, this helps, but it's unclear if it helps enough. Next example, I want to start by showing you yet again another movie. I think this one's really great. So this is showing the late time evolution of a Milky Way mass galaxy. Right about here, satellite is going to crash into the disk. Now we'll fly through the disk, see GMCs, young stars as bright blue points. Now we're going to fly out. You get to see the nice dust lanes that we see in these simulations. This is all done to look like HST, but what I want you to notice is that as we go all the way out, there's no more satellite, right? Instead, there's this stellar stream. That satellite was destroyed by that interaction with the disk. And importantly, a gravity-only simulation does not include a galaxy, right? Because I have to paste galaxies on top of my gravity-only simulations. So in other words, when you run a gravity-only simulation, you're not even getting gravity correct, because you're missing the gravity from this galaxy at the center of your halo, right? And that turns out to be a pretty important effect. So we showed that if you take a gravity-only simulation and you add a disk, an analytic potential to the center of your halo that models a disk galaxy there, then you get really good agreement with a full baryonic physics run. And then we were able to say, based on that agreement, that the Milky Way disk alone is responsible for destroying about 25% of all subhalos, and about 75% within about 50 kiloparsecs of the galaxy center, right? This includes those massive subhalos that are associated with the central mass problem. So again, we're destroying about 25%, that means there's 75% left, so this helps, but it's probably not enough. That said, this has enormous implications for things like finding dark subhalos via gaps in stellar streams, or via lensing anomalies, so I'm happy to talk about those offline if you're interested. Finally, maybe it's pointing us to new dark sector physics, right? So a lot of people have postulated, they've said, okay, well, if these galaxies are so low mass that their baryons can't do anything to the dark matter halo, then maybe we need to modify the dark matter halo some other way. So as an example, with Oliver Elbert, we looked at self-interacting dark matter. So the basic idea here is that dark matter particles have some scattering cross-section. When they come close to one another, they have a chance to bounce off. In this case, we're just doing billiard ball kinematic scattering, basically. What this does is adds a little bit of pressure to the dark matter. We effectively get a pressure force in the dark sector. So that can act to buoyant out your dark matter, right? So on even large-ish 50 kiloparsec scales, there's no difference whatsoever. So as we make the self-interactions more common, you get the exact same structure on sort of the halo scale. When you zoom in on the scale of a dwarf galaxy, so this is showing basically the red region for each of these points in the upper panels, you see a huge difference where you go from this dense cusp to a central flat density core, basically. So we showed that this solves the central mass problem without fine-tuning any of the parameters. But I'm perfectly willing to admit that self-interactions fall in the regime of exotic physics, and new physics require extraordinary claims, right? So we ought to rule out all of the rest of the possibilities first. So that brings me to sort of a summary of this, which is saying that some type of other physics are important to the formation of these galaxies. It could be known physics, as say baryons, like supernova feedback, tidal interactions with the host or with other galaxies, It could be just halo-to-halo variance and how many stars you form in a given halo. Or this could be pointing us to exotic new dark matter physics, basically. So it could be self-interactions, could be some changes to the initial conditions that I showed you, could be scalar field dark matter. We're not quite sure about that, but we're still thinking about it. So the question then is, are known physics, or baryonic physics, enough? When we add the baryonic physics that we know exists to one of these cosmological simulations, can we reproduce the local group dwarf galaxy population? Now, in order to answer that question, I basically need a simulation like the gravity-only simulations I showed you earlier of an entire local group run in a cosmological setting, but now I need to add baryonic physics to it, right? Turns out I have just such a simulation for that. Wow, this looks great on that projector, actually. So this is the 3D dark matter density from the next generation simulations of the local group that I promised you. We're calling this Elvis on fire because it's exploring the local volume in simulations, and we've set it on fire by adding the feedback and realistic environments models for star formation and stellar feedback. So that means we have hydrodynamics, of course, but we also have gas cooling all the way down to 10 Kelvin. We have star formation, and then stellar radiation such as photoionization, photoheating, and radiation pressure. And most importantly, we have stellar winds and supernovae, right? So when stars die, they do things to their environment. And I want to make the point that these are actually, this simulation in particular is actually the highest resolution cosmological simulation of a Milky Way mass galaxy with hydrodynamics ever run to redshift 0, which is a huge spiel with a bunch of caveats. So the takeaway is that this is the highest resolution and most realistic sim of the local group ever done, and the best simulation for tackling these problems ever run. Okay? I don't think anyone would take issue with that. Now you might ask, why didn't people do this before, right? This is an obvious thing to do. Well, it's incredibly expensive. So they take about 15 million CPU hours per simulation, which is the equivalent of one computer running for about 2,000 years. So these take a lot of time and a lot of computational energy. So let's dive into them now. How well do we do? Are we able to reproduce a local group dwarf galaxy population? Before I show you that, I love to show this fade. So here, like I said, I'm showing the 3D dark matter density. Now I'm going to fade into the stars. What you can see is that we went from a picture where we had an enormous amount of structure, right? Here, every single point that you see here basically is a collapsed dark matter halo. When we go to the stars, most of those halos don't have any galaxies. Like this picture is completely blank down here, right? Excuse me. So this speaks to the missing satellites problem, right? The vast majority of our dark matter substructure does not host an observable galaxy. So let's quantify that statement. Oh, sorry, before I move on to that, I want to emphasize again the enormous dynamic range that we're resolving here. So this entire image is about 2 megaparsecs across. If I zoom in on the central sort of 40 kiloparsecs of each of these, then we get these nice host galaxies. Again, these are false color images, but the point I want to make is these are very realistic simulations, right? We're forming realistic looking galaxies with dwarf populations around them. Okay, so let's quantify our statement about the missing satellites problem. This again is a stellar mass function, stellar mass on the x-axis, number of galaxies on the y-axis. The observations, Milky Way and Andromeda, are already plotted on here. Let's put that galaxy, or that run, which I'm calling Romeo and Juliet, on here. Looks great, right? No missing satellites problem. We even have fewer than Andromeda. We also have another local group. I'm calling that Thelma and Louise. I can put that on here too. Again, looks great. Scatters basically about the observations for the Milky Way stellar mass function. Now in Fire, we also have a set of 8 isolated Milky Way mass galaxies. So I'll go ahead and put those on here too. These are at marginally worse resolution, but it's basically the same. And again, we scatter remarkably well around the Milky Way stellar mass function. So, in other words, there's no missing satellites problem in these simulations. Now you might notice, okay, Andromeda is a bit higher than all of your lines, right, than all of your predicted lines. I'm not too worried about that. I think this is probably just a halo mass thing, but I'm happy to talk more about that offline later. So what about the central mass problem, though, right? I told you in a gravity-only simulation we could reproduce the stellar mass function fine, but we did so by matching galaxies with subhalos that couldn't actually host those galaxies because they had the wrong mass profiles, basically. So again, if we look at this simulation with no baryonic physics, gravity only, we find the central mass problem. So we find a whole bunch of subhalos that have too much central mass to really host anything other than basically Draco, the highest density dwarf galaxy around the local group, around the Milky Way. If we turn on baryonic physics, we add supernova feedback, we add hydrodynamics, we add all these incredibly expensive and difficult things, but things that we know exist in the standard model, to this simulation, then we turn all of these lines into lines that look like this, right? So, no central mass problem. All of these lines are broadly consistent with basically all of the dwarf toroidals observed around the Milky Way. And just to show you that again, we go from points way up here to looking like this. So, to make this point very strongly, cosmological baryonic simulations can reproduce the Milky Way dwarf satellite population over a statistical suite of simulations without invoking new physics. I only showed you one host there, but I could show you all the other 11 in Fire that we have. None of them have a too big to fail central mass problem. Okay, so we're done, right? No, of course we're not done. Right? So first of all, I've only convinced you that this is true in terms of the number of galaxies and the central masses of those galaxies. I haven't said anything about, for example, their metallicity or their distributions in space. I'm happy to talk about those things offline. I'm not going to talk about them in the rest of this talk. And I also haven't talked about M31 at all, right? So we have not only the Milky Way and its satellites, but we have Andromeda and its satellites. So why not look at those? Well, so if we pull up M31, here I'm applying the same subhalos from before, just for consistency, basically. Then you'll see that again, okay, we have some systems up here that any of these could reasonably host. And then there are a few of the dwarf spheroidal galaxies that match up with our gravity-only simulations, but the majority of our dwarf spheroidals are down here and have no clear observed analogues, right? No clear simulated analogues. And then we turn on baryonic physics. And again, we shift from a picture where all our lines are sort of in this regime to a picture where our lines are down here and do a very good job of matching the observations. But now we're left with this category up here, right? Now we're left with this chunk of 3 or 4 galaxies that are way too dense to match with any of the simulations. So this is the opposite of the central mass problem, in that now our simulations are underdense relative to the observations. Excuse me, and again, I'm only showing you one host, but trust me when I say that all 12 of the Fire Milky Way mass galaxies suffer from this problem. And we've also looked at this in terms of isolated galaxies simulated with Fire, and again, they tend to have lower central masses than these observations. And you might say, okay, well, you didn't have enough galaxies around your Andromeda, so maybe it's just a halo mass thing, right? Or maybe it's a stellar mass thing. Maybe your galaxies aren't big enough. Well, actually...
Sorry, quick question.
Yes.
So if you do SIDM, does that help? Or do you also see the same problem?
I would like to talk to you about that offline, to be honest. I think it could help, but I think it could also hurt. So we need to run the simulations and see, basically. And I'll talk about why I think that later. So it's possible that we just don't quite have the right galaxy population to match Andromeda, right? But these are our biggest satellites. These are all around 10 to the 8 in stellar mass. And if I pick out the biggest simulated satellites on this plot, then those are these 2 white lines, which you can see actually have less mass at, say, 300 parsecs than a lot of their lower mass analogues, right? So this is, again, supernova feedback at these masses is very effective at removing dark matter from the center of your halo. And in fact, I can put this plot back on here, right? So remember here we're looking at stellar mass along the x-axis and less dense galaxies up here. These galaxies at 10 to the 8 fall right around this regime, right? So it's not even just Fire. Several other simulation groups are finding the same thing, that we're not sure how we make these very high density dwarf galaxies at about 10 to the 8 stellar masses and these much lower density dwarf spheroidals at 10 to the 5 to 10 to the 7. I'll also note something like M33, is even a little more massive, and as you can see, it's nowhere near as dense as a lot of these systems. So these are definitely strange objects. Okay, so before I move on, how much time do I have left? Okay. Okay, great. Before I move on to sort of what's next, I want to answer a question that you might all be asking. Why are we simulating the local group, right? I told you these are very expensive. They're about 15 million CPU hours each. An isolated Milky Way takes about 5 million CPU hours. So in other words, we're spending about a third of our time not simulating the systems we care about, right? So why do this? Is it worth it? Well, it turns out, so here I'm plotting the normalized star formation history of dwarf galaxies here between 10 to the 6 and 10 to the 7. And I'm taking the median in this thick white line of all of the dwarf galaxies as satellites of our local groups. And then the thick green line plots the median of the satellites of the isolated Milky Way simulations. Okay, these look basically the same to me. There's maybe a tiny bit of deviation up here, but that's well within the 1 sigma scatter indicated by the dashed lines. So in other words, it doesn't matter for satellites. The local group environment, as far as we can tell, is completely irrelevant for satellite galaxies. And we showed this before with the with the gravity-only Elvis simulations. Again, satellite populations were exactly consistent between the paired and non-paired samples. However, when we look at non-satellite galaxies, if we look beyond the virial radius, outside 300 kiloparsecs from the local group, from the Milky Way, then we do find differences. So this is again the exact same thing, but I'm just looking at non-satellites around local groups and non-satellites around isolated Milky Ways. And here you can see there is actually what I'm not going to show you the plots, but trust me when I say that this is actually a statistically significant offset between these two median lines, right? So in other words, the local group environment, for some reason or another that we're still trying to get a little bit of a handle on, inhibits late-time star formation in dwarf galaxies nearby, relative to an isolated Milky Way mass host. Now again, this is only true when you look at non-satellite galaxies, but importantly, upcoming surveys like LSST are going to probe non-satellite galaxies. So, in other words, if you want to study non-satellites in the local group, you better simulate local groups, or at the very least account for this bias in your work. Okay, so 10 minutes or so left. What's next? Where do we go from here? Where's the field moving to? Well, I've mentioned LSST a couple times, so I want to motivate that real quick with this plot. So this is plotting the number of known galaxies as a function of year, right? So a lot of you are probably familiar with this uptick at late times around the Milky Way. This is, of course, the Sloan Digital Sky Survey, SDSS, turned on in 2005, and was able to survey a big chunk of the northern sky to unprecedented depth, right? And with that data, we found an incredible number of new, what we called ultra-faint dwarf galaxies, so very faint dwarf galaxies. Then we can put a line on here for Andromeda. Andromeda has a similar uptick around a similar time, but this is actually not because of SDSS. Andromeda is too far away for SDSS to help. Instead, this is targeted surveys like Pandas and Splash. Andromeda is relatively small on the sky because it's far away from us. So we can point the telescope and tile that whole area, if we have enough telescope time at least. However, if we put non-satellite dwarf galaxies on here, then there is no uptick, right? This is just slowly chugging along. Every so often we happen to find one. And the reason is because these are too far away for Sloan to help us, and it's too big of a sky for us to do targeted surveys, right? We basically need to do a targeted survey of the entire sky. Well, fortunately, LSST is going to effectively do a deep survey of the entire sky. And I doubt I need to tell you guys here too much about LSST, but I find it absolutely remarkable. So it's basically taking the best telescopes in the world today and using them to survey the southern sky. So it's going to be capable of doing this every 3 nights. I don't know what the actual plan is. I'm not sure if the actual plan is decided yet. But we expect this is going to find a lot of new dwarf galaxies, particularly in the local field. So not satellites of the Milky Way or Andromeda. Now LSST is only photometric, so once we identify those dwarf galaxies, we're going to want to follow them up, both to get metallicity, but also to get kinematics, and to ensure that they are actually dwarf galaxies in the local group and not something really far away. So for that, we're going to need 30-meter ground-based telescopes. So GMT, ELT, TMT, these are all things that are either in the process of being built, in the process of getting their funding secured, or I think GMT actually is taking data very soon. Now, of course, it's not all ground-based. We also have space-based missions coming up. So JWST will launch sometime, hopefully 2020, fingers crossed. And JWST, I like to think of JWST as sort of a Hubble with an incredibly big mirror. So JWST is going to allow us to see much deeper and much more precise details than Hubble let us see, basically. Then, about 5 years later, again, fingers crossed, probably closer to 10, 20 years later, the Wide Field Infrared Survey Telescope, WFIRST, is going to come online. WFIRST, so wide field is not at all a misnomer. This image here is showing how many pointings it took to tile the Andromeda disk with HST versus how many it would take with WFIRST. Right, so this is, again, just mind-boggling to me. So like I said, JWST will map small and far-away details, while WFIRST will map enormous fields. So I love this movie. This is the Hubble Ultra Deep Field. And this is what the WFIRST Ultra Deep Field would look like. And it keeps going. So yeah, I love this. I think this is incredible. So this is going to be great for things like stellar halos of nearby galaxies, or even just tiling portions of the sky. I think this is going to be absolutely incredible. So with all these awesome observations and awesome telescopes that are going to be coming online, how are we as simulators in particular going to keep up? In particular within the FIRE collaboration, I should say. Well, number one, we need more simulations. We need bigger samples. We need to beat down halo-to-halo, host-to-host variance. So this will come. We're working on it. We also need more physics, right? Because we know that even though these simulations are pretty good and they have more physics than, I would argue, the majority of cosmological simulations to date, they're still incomplete. So reionization is basically an ad hoc prescription. It's just a background that gets turned on. So maybe we can more realistically model reionization. I'm interested in how we can maybe put in even semi-realistic models for population 3 stars and model the distribution of metals to the intergalactic medium. We might need to, well, we definitely need to add a model for active galactic nuclei. We don't currently have one, which is why we don't run simulations of more massive galaxies than the Milky Way, basically, at least not to redshift 0. But we also might need to add magneto or radiation hydrodynamics. This is work in progress. Or cosmic rays. So, for example, this is showing the circumgalactic medium of a Milky Way mass galaxy in the standard FIRE simulations. This is, in fact, one of the galaxies I showed you guys earlier. Again, purple is cold gas, green is warm gas, and red is hot gas. If I turn on, well, not I, but if we turn on cosmic rays, then we find this picture instead, where an enormous amount of that hot gas has been replaced with this cool gas instead. So the CGM is a lot cooler when you turn on cosmic rays, because effectively those cosmic rays are able to hold up cool gas that would otherwise fall onto the galaxy. Your galaxy also ends up slightly smaller, of course. So this could have enormous implications, for example, on the satellites of this system that are flying through this now very cool CGM, rather than this previously very hot CGM that was presumably better at, for example, ram pressure stripping them. We also need to ask what non-standard dark matter models, together with baryonic physics, predict. Right? So there's a long history of running dark matter gravity-only simulations with non-standard dark matter models, but ignoring baryons, because baryons are difficult. Well, it turns out that when you put these two together, then you can start to make robust predictions for what these for what these models will do. So here's a plot from Victor Robles' 2017 paper that I really like. This is showing the density profile of a very small galaxy, 10 to the 5 solar masses. And in solid are the predictions from the standard cosmological paradigm, collisionless dark matter. So this galaxy is small enough that even when you turn on baryonic physics, even when you turn on supernovae, etc., you get the same exact density profile. You're not able to form a core in this galaxy. However, in SIDM, you get a core no matter what, right? Because the dark matter alone is able to form a core. So in other words, if we can actually measure a density profile within about 500 parsecs of a very small dwarf galaxy, then we can actually put robust constraints on the scattering cross-section at these low velocities. Now we're also going to need to tackle these simulations with more imagination. Right? So we need to think about how we can use them in new ways. For example, creating mock catalogs so that we actually observe the simulations rather than treat them as all-knowing. Applying machine learning, so we're thinking about how we can apply machine learning to the stellar halos of these simulations, for example. And even adding models for gravitational waves, in particular binary neutron stars, which have a possibility to enrich the circumgalactic medium directly. So that's something possibly very exciting. And then finally, we need more power. So we need higher resolution, right? This is going to allow us to resolve smaller galaxies, the ultra-faint galaxies. In all my previous plots, I basically cut off at about 10 to the 5 in galaxy mass, right? And it'll allow us to reduce our reliance on subgroup physics, ideally. So as an example, next-gen hydrodynamic simulations. We've been running, so far I've been telling you about the Elvis on fire and the Latte simulation. So these have baryonic particle masses, 3,500 to 7,000 solar masses, which means we get about 100 million particles in the halo, and these cost between 1 and 15 million CPU hours, depending on the galaxy, how well you're able to make your initial conditions, basically. What we're working on is what we're calling triple Latte. So triple Latte is going to have baryonic particle masses of 900 solar masses, which means we get about 1 billion particles in the halo, and this is going to take about 25 million core hours. But it's currently running, it's already about halfway done, and we're already getting cool stuff out of it. So for example, this is our Milky Way mass progenitor at redshift 2.5 at about the depth that HST could go to. Excuse me. And in fact, if we go and look in HST, we can find images that look kind of like this. Cool, right? However, this is all the structure that you're missing. If you go down to fainter surface brightness, all this incredible stuff pops out. And something like JWST should be able to find something like this. Okay, so I'll end with my conclusions here. I would argue that dwarf galaxies uniquely constrain dark matter and galaxy formation, but that new simulations with known but very difficult physics can at least broadly reproduce the dwarf galaxy population in the Milky Way, although we're still running into some issues capturing the full diversity, particularly with regard to the Andromeda satellites. And of course, these new / upcoming observations are going to require unprecedented simulations that let us tackle these in new ways. Finally, feel free to ask me about some other work that I've done that I didn't quite have time to talk about. So for example, morphologies of Milky Way mass galaxies, gravitational wave signals, non-standard dark matter that we've done so far, or if you're interested, have you looked at Blink with fire? Happy to answer any of those questions too. All right, thank you guys again.
Questions for Shea?
Can you go back to the Andromeda satellite purple plot?
It's gonna be quicker. This one?
Yeah. So, okay, I understand physics. Gravity. And I know why all of your white curves go in the direction that they do. But your purple points don't have X error bars, but there's only one per galaxy, I think, in most cases. And if I were to look at that as a scatter plot and draw lines on it that fit, I would surely draw them exactly perpendicular to what you've got there.
Yeah, so
why isn't that telling us something about the density of galaxies as a function of their size?
It might. So each point here is a single galaxy. Right? So there's no necessarily correlation between the points.
Yeah, I understand that, but I mean, that doesn't mean that the size of the galaxy doesn't tell you something about the correlation between dark matter mass and stellar mass.
That's right. So I haven't shown you, for example, R half, which is the X value plotted here versus, say, stellar mass. The reason I didn't show you that is because we're not quite recovering that, basically. So we think that's probably due to resolution, that at the low end down here, we just struggle to get half of our stars inside that radius. So at higher masses and at higher R1/2, we do a pretty good job of capturing that structure, but not so much.
But but you're tuning your simulations at some level. Well, sorry, you're attempting to include things in simulations so that you shift either the width of those white curves, right? You increase or decrease the width, or you shift them up and down. And it's like, well, the width of the white curves to cover everything on there has to
The scatter, basically, yeah.
It has to encompass everything. So why isn't there something else that tells you, well, there's a trend going in the other direction?
So you would expect that there would be some trend with stellar mass or something, but it's not clear what exactly that trend should be, because you basically have two effects fighting against each other. So a bigger galaxy probably lives in a bigger halo, right? So that means this rises more steeply, but it also should be more effective at creating a core in that halo, which tends to make this rise more slowly. So really, you can kind of see what is happening. These are the two most massive galaxies, right? So they do live in their biggest halos. But at the center, the baryonic feedback has been enough to strongly modify. Is that getting at what your question is? I might be misunderstanding what you're asking.
I guess all I'm saying is, has anybody considered models which would give you a stellar halo mass dependence that's actually a function of size, or in other words, a density effect, which would give you a distribution that naturally reproduced the curve that's sort of perpendicular, even though I understand those are different galaxies.
Yeah, so we have a late stage draft basically right now looking at isolated dwarf galaxies, so no Milky Ways in the simulation. That enables us to get a much higher resolution. That does a better job of capturing R1/2, M star, V1/2. That's sort of, that's the 3D plane that you want to match stuff in, basically. It's not clear if we're doing it well yet, because we don't have enough galaxies in those simulations. We're arguing, so that particular paper, it's Alex Fitz et al., hopefully coming out in a month or two, keep your eyes out. That particular paper includes a bunch of different dark matter models, so that includes self-interacting dark matter and warm dark matter. But we can't really tell if either of those do a better job or not yet.
Is it possible that there is some underlying known physics which actually depends on the halo mass, which can be inputted into the simulation?
I think it's always possible that there's underlying known physics, but I'm not able to think of any off the top of my head that we're not including. So there are physics that depend on halo mass. For example, the hot halo, that hot gas halo is something you only get when you get to around L star. Dwarf galaxies can't support that. So there are changes that happen as you go to higher stellar masses, but I'm not sure what we'd be missing in that regard. Well, cosmic rays.
This one is there anything that can be included which depends on the mass and can resolve this?
That can resolve this? Not that I've thought of yet, but I'm very much open to ideas, because I think this is a difficult problem to solve.
So obviously I have an interest in this, but it's interesting that you have two realizations of dwarf systems and they pull in completely opposite directions if you look at this plot, right?
Ah, yes. Yes.
So the Milky Way, for a while people were going in one direction because the Milky Way said do this, and then if you look at M31 satellites, it just takes you in the opposite.
Yeah, I think a lot of the M31 satellites, right, still try and pull you down.
Yeah.
But the problem is that you also have these up here, and again, there's a very high mass. So we sort of ignored those in the past because we said, okay, these are baryon-dominated within the half-light radius. They have more baryons within our half than they do dark matter, which means that we know that we can't model them in the dark matter-only simulation. So we didn't even try. But now that we have baryons, we ought to be able to reproduce these, right? And we're not.
Well, that's a little bit like to, rehash old history, the angular momentum catastrophe, which was like, okay, we're going to study disk galaxy formation in dark matter-dominated galaxies because that's an easy probe.
Yeah.
But then all of our ideas fail completely when we try to actually model a galaxy that has baryons in the center, which most do. So,
by definition.
Nico and then Peter.
Yeah. And so, do you have a sense of what baryonic physics process affect more, to solve the central mass problem?
Yeah, so I didn't show a plot about this, but so I would say we only solve the central mass problem with respect to the Milky Way satellites. I would argue that we alleviate the central mass problem in the local field, which I didn't show you guys, and in Andromeda it's a mess. Excuse me, so in a gravity-only simulation, all your lines are up here. When you turn on baryons, they're basically, there are three main effects that occur. So number one is supernova feedback. We actually argued that while that happens, for sure, so supernova feedback creates core formation, we argued that while that happens, and we do see evidence that that happens in the fire simulations, it's not actually necessary. So numbers 2 and 3 can resolve this problem alone. So number 2 is mass loss. So effectively, in this gravity-only simulation, it's somewhat technical, but you're basically locking all of your baryonic mass onto a dark matter particle. You just lump all that together and say this all acts like a dark matter particle does. But in actuality, these galaxies are something like 1%, 10% at most the cosmic baryon fraction. So most of that baryonic mass that you locked onto your dark matter particles should not be there. So that brings you 15% down, basically. Number 2 is a tidal destruction, right? So you're able to destroy a lot of the satellites that otherwise are problematic. Or you strip them more than you would have otherwise, and they end up smaller than you would have predicted. So we found that if we take these lines, and we go to very large radii, basically Rmax, and then we assume dark matter-like density profile, specifically an NFW density profile, you still do not find a central mass problem. So if these lines looked like NFW profiles, they'd still fall off sharply enough that we wouldn't find the central mass problem. So in other words, core formation happens, but you don't need it.
Peter, last question.
Yeah, so if you have a core, then there's less of an incentive for the galaxy to sit at the center of the dark matter.
That's a good point.
So could you say a bit about how centering does or does not affect this issue?
In the observations or the simulations?
Both, yeah.
In the observations, I don't know if it matters, to be honest. Thinking through the Wolf et al. Formalism, I guess if you get your R half wrong, so if you get your half-light radius wrong, then that would enter into it. And that, I guess if you got the center wrong, then you'd be more likely to get your half-light radius wrong. Which way would that go? Let me see. So if you were off-center, your half-light radius would probably be estimated to be too big, if I remember right. Yeah.
Sorry, so just make sure I understand. So the curves are plotted from the center of the dark matter halo or from the center of the actual galaxy?
In this case, the curves are plotted. I don't remember. I'll have to check that. I think they're plotted from the center of the halos. I'm not positive. In practice, what we found is that the dark matter, the dwarfs tend to be at most like half kiloparsec off in the center of the halo. Now that said, half kiloparsec is here, right? So that's not a negligible effect. I should check that and make sure. Yeah, good point.
Great. Well, thanks, Jay, again.